cutoff for the exam to be at the end of this lecture. Just a couple of announcements. A few of you do the exam in another room, and you're given more time, and you have to give me a special form. Please make sure that I have that form. I think I've received, it's a yellow form. I think I've received only one yellow form so far. So make sure I get those forms. The next thing is that what I did was to type up a summary of the essential things that you've been taught in Chem 263, and I asked the IT people, what's that, information technology people, these guys who work the computers for us, to post this on something called eClass. And so if you access it, I think you're supposed to know how to access eClass. I gather there's a course that teaches you how to access eClass. If you go to eClass, you'll be able to find a nice little summary that deals with the essential details of NMR that I've taught you, and the stuff about conjugated systems, and the stuff about aromaticity, and also about aromatic compounds. At the end of that, you'll also find, somebody asked me to tell them which pages of the various chapters I'd covered. So I was able to do that for the volume 10, but it's a bit too difficult, I think, to do for edition 9. Then there are 2 help sessions. This Friday, the 14th at 5 o'clock in this room, you'll get a super TA help session. Very clever TA, knows everything. And I believe on this Thursday, also in this room, I've forgotten what time I said. 5:45, okay, let me write that down.
I thought it was a makeup class, not a help session.
No, it's help session. There's no makeup class until after.
All right.
Should we have the Friday one at the same time? Later?
Earlier.
5? Why don't I make it 5:15? Right.
5:15.
5:15.
Friday's 5:15.
Okay.
The Thursday's 5:45.
I think those are all the announcements. And now what I want to do is to continue what I was talking about last time. And right at the end of the last lecture, I was dealing with the Friedel-Crafts alkylation and the Friedel-Crafts acylation. And I pointed out to you that the Friedel-Crafts acylation has a very nice advantage over the alkylation in the sense that once one acyl group has gone on, the reaction stops. Whereas the Friedel-Crafts alkylation, you sometimes get more than one alkyl group going on, and you can take advantage of this because if you take a typical Friedel-Crafts alkylation product, and you heat it with zinc in hydrochloric acid, what happens is that the carbonyl group, that's this, the carbonyl oxygen, is replaced by 2 hydrogens. So now this is exactly the product you would get from an ideal Friedel-Crafts alkylation. And sometimes it's a lot better to do the Friedel-Crafts acylation followed by reduction than it is to do the Friedel-Crafts alkylation. Another thing that you need to know about the Friedel-Crafts reaction is that you can do it intramolecularly. For example, oh, this is useless. If you take a compound like this and you treat it with thionyl chloride, what you will get is an acid chloride, and if you treat that with aluminium trichloride, then you might think that you would get that. I'm so sorry. I missed something out. Zinc and HCl. What you will get is the compound that I've shown. And clearly what has happened is we've converted this. Actually, you can do it different ways. I'm kind of sorry. If you do the Clemmensen reduction first, then you'll get CH2 there. If you then convert the acid with thionyl chloride, you get an acid chloride, and if you treat that with aluminium trichloride, you get an intramolecular Friedel-Crafts acylation. Now this word intramolecular is used to mean that it's within the same molecule, as distinguished from intermolecular. You know the word international, between nations. So intermolecular is between different molecules. And if you take, say, benzene, and you treat it with, say, acetyl chloride and aluminium trichloride, you're carrying out an intermolecular, that's intermolecular, and this one is intramolecular. So you can do the Friedel-Crafts acylation intermolecularly and also intramolecularly. Now, the last topic that I need to cover for the exam, it's also the next topic in the normal schedule of things, is I have to tell you what happens if you have one or more substituents already present on a benzene ring and you carry out an electrophilic aromatic substitution. Now you already know if you take benzene and you treat it with concentrated nitric and sulfuric acid, you'll get nitrobenzene. That's a simple electrophilic aromatic substitution. One of the hydrogens is replaced by a nitro group. You also know if you treat benzene with acetyl chloride and aluminium trichloride, you'll replace one of the hydrogens by an acyl group, Friedel-Crafts acylation. If you take an alkyl halide and aluminium trichloride and benzene, you'll replace, to begin with, one of the hydrogens of benzene by the alkyl group. That's Friedel-Crafts alkylation. You can also do a sulfonylation. You can do a bromination, a chlorination. So all these examples I've given you so far of electrophilic aromatic substitution have started off with benzene, and you've got the result was replacement of one of the hydrogens by the electrophile, by SO3H, NO2, acyl group, alkyl group, chlorine, bromine. But I hinted that things can be a little more complicated when I talked about the Friedel-Crafts alkylation, because I said that the first product that's formed once an alkyl group has been attached to the benzene ring is more reactive than benzene, and therefore you very frequently get what's called polyalkylation, which just means that many, 2 or 3 or 4 or 5, even 6, I suppose, alkyl groups go onto the benzene ring. And I also told you that in contrast to the Friedel-Crafts alkylation, the Friedel-Crafts acylation produces a substance which is less reactive than benzene, and therefore once one acyl group has gone onto the benzene ring, the reaction stops. So having told you that, that sort of, in a very vague way, tells you that once you've got a substituent on the benzene ring, the ring can be less active or more active. So that's the first complication. Once you have a substituent on the benzene ring, and you try to do another electrophilic aromatic substitution, you will find that depending on the substituent, the ring will be either more reactive than benzene or less reactive than benzene. There's a second complication which is much more important for you, because if you're doing an electrophilic aromatic substitution on a substituted benzene, if it's less reactive, you just have to stay longer in the lab because the reaction's slower. If it's more reactive, you can finish your experiment quicker and go home early, watch a movie. Or preferably study the chemistry textbook. There's a much more important complication, and that is when you have one substituent present on the benzene ring, not only can it alter the reactivity, more reactive or less reactive, but it also directs the second electrophile to certain positions on the benzene ring. You see, when you do an electrophilic substitution on benzene itself, all 6 positions are identical. But once you have one substituent present on the benzene ring, the substituents are no longer identical. And so what I need to tell you in the next 30 minutes is what substituents make the ring more active, more reactive, what substituents make it less reactive, and for these various substituents, where on the ring do they direct the incoming electrophile? So I'll clean the board and I will explain all that. It's not difficult.
Still what happened? You have a locker?
I'm gonna get one.
Which one's
I'm not sure I have it. Last thing here, so we'll do that.
You can categorize all of the substituents into one of 3 classes. So one group of substituents activates the ring. In other words, if that's it, one of those substituents is present, the ring reacts faster than benzene. And the next electrophile, the second electrophile, goes into the ortho and para positions to that substituent. So the question is, what are these substituents? Alkyl groups are a member of this class. So all of these are activating groups and ortho-para-directing groups. So if you have any of these substituents present on a benzene ring, I'll just write up one example. Let's take a very simplest example. This substituent clearly is an alkyl group, the first one that I wrote down. If I do an electrophilic aromatic substitution, let's just, for example, say that it's nitration via that nitronium ion. What I will get is a mixture of two compounds. Because the alkyl group is an ortho-para-director. So it directs the incoming electrophile to the ortho position, which I'm pointing at. Of course, there is another ortho position, but by symmetry it's the same. And it also directs to the para position. So you get this mixture of two compounds. Now you might want to know which is the predominant one. Answering that sort of question for these electrophilic aromatic substitutions is rather too complicated for this course. So as far as you're concerned, these things are ortho-para-directors and you get a mixture. You will get substantial amounts of both of them. It's not going to be like 99 to 1. It might be 60-40 or something like that, or 50-50. So any member of this group as a substituent will direct ortho-para. So it's very easy. If you have any other substituent, let's just take this one, say. You don't have to write this down, it's so obvious. You see, the substituent is in this list. Now, you might be thinking, oh my God, I've got to commit this list to memory. Oh, holy smokes, and I want to play hockey tonight, and I haven't got time. And there's a movie on, and I can only study for 5 minutes. That's not enough time to commit this to memory. You might be grumbling to yourself. But there's a trick. There's a trick. Let me show you. You will notice something.
It's not the N's, not the O's. Did you notice that?
Kind of.
I just saw the N. Oh.
With two exceptions, all these babies have lone pairs. You also know from Chem 261 that alkyl groups are electron donating. That's why if you have a carbocation, a positively charged carbon, the more alkyl groups it's got on it, the more stable it is. Because the alkyl groups push electron density towards the carbocation, stabilize it. So it's not a real imposition to memorize this stuff. In fact, you don't have to memorize it. If you see a substituent that's got a lone pair on it, it's pretty likely that it's going to be an ortho-para directing group and an activating group. Now, why it should be activating, I'll mention very briefly, and probably I won't have time to go into it in detail today, but I'll certainly do it on Friday. All of these things can push electron density into the ring that's undergoing electrophilic aromatic substitution. So if you know from what I told you about electrophilic aromatic substitution of benzene, that what happens is, I deliberately used this childish expression, I said the electrons leap out onto the electrophile. I use that so that you'd remember it. Now if they leap out, obviously if you're shoving electron density into the benzene ring, they're more likely to leap out, because there's more of them there. So that's why these are activated. Now, either at the end of this lecture or certainly in the next lecture, I'll give a full explanation. And what I will do is I will write resonance structures for the intermediates. And you will see that all these substituents can very easily stabilize the resonance structures if the electrophile attacks ortho and para. And you will also see that all these substituents can shove electron density into the ring. But at present, I just want to show you what the facts are. So I said that there are three groups. This is one of the groups, activating and ortho-para directing. So I'm going to clean the board. It looks to me like only the two middle boards are visible to everybody. Why they didn't make, the board sort of around a little bit so that everybody could see, I don't know. As far as I'm aware, the design of lecture theatres or amphitheatres is a few thousand years old, but I guess the architects still haven't learned how to do it properly. Now, the second group
I haven't started yet because I have a midterm tomorrow. What about you? It's like lots of memorization. It's the one thing I hate. What about you? How's studying going? Very boring. Reading a textbook is so boring.
This is the second group. And again, it's not a very big imposition. In fact, it's no imposition at all for you to commit this to memory, because it's the halogens. Fluorine, chlorine, bromine, iodine, and also the CH2Cl group. So these are the main members of a relatively small group of ortho-para-directing and deactivating. The vast majority of activating substituents, that is to say substituents that can push electron density into a ring, are ortho-para-directing. And the vast majority, as you'll see in a moment, of substituents that suck electron density out of the ring are deactivating and meta-directing. But this very small group are deactivating, but nonetheless ortho-para-directing. So what does this mean? Let me take again a trivial example. And let's do a nitration. So if you do this experiment in the lab, you'll find it goes slower than in the case of benzene, because these things are deactivating. But the product mixture that you get will be the result of ortho substitution and also the result of para substitution. So now, if I were to write up a benzene ring with a substituent on it that is a member either of this class or of the class that I put up a few minutes ago, and I asked you what would happen if you did a mononitration or a monosulfonation or a monoalkylation or a Friedel-Crafts acylation, etc., etc., you'd be able to write down what the products are. Because in both cases you get author substitution and para substitution. And there's one other class, for which again I must clean the board.
Is it meta deactivated?
Possibly. I've been reading it every day.
No. I'm only on like an MR.
I need to start that. I'll go through that after.
Whole chapter. I think my notes are making a lot more sense compared to when we first started. I was like, what are we doing? Unlike Ben's part, yeah. What chapter is this?
Well, it's to do question 714.835, the same chapter.
He said he would post up more info on where we were. Some of the other chapters, it looks like he covered them. Part of them.
All of these are deactivating and meta-directing. Now, when I say they're deactivating, obviously that means that they react in a given electrophilic aromatic substitution more slowly than benzene. And the substituent goes into the meta position with respect to the substituent. So let me again write up a trivial example. And supposing I do a nitration. It's going to be slower than in the case of benzene. And that's what you're going to get. Now, I'll just give you a moment to copy this list down. And then I'll tell you a few things about this list. You remember that I told you that if you do a Friedel-Crafts alkylation, you very frequently get poly substitution. If you look back over the notes that you've made in the last 10-15 minutes, you will see that an alkyl group is an activating group. It's activating and ortho-para-directing. So if you take benzene and do a Friedel-Crafts alkylation, once one alkyl group has gone onto the benzene ring, you now have an activating ortho-para-directing group present. Since it's an activating group, it means it reacts more quickly than benzene. So it's no surprise that you will get polyalkylation. And of course, once a second alkyl group goes on, you've got two activating groups. So other things being equal, which they're not quite, the thing will get faster and faster the more alkyl groups you've got on. Doesn't quite happen like that, but it's very understandable that Friedel-Crafts alkylation gives more than one alkyl group stuck onto the benzene ring. But if you look at this, which is a ketone, you see, this is the result of a Friedel-Crafts acylation. And I told you today, and I told you in the last lecture, that Friedel-Crafts acylations have this very nice characteristic compared with Friedel-Crafts alkylations, in that the acylations stop after one acyl group has gone on. And guess what? An acyl group is a member of this class of substances that is deactivating. So consequently, if you take benzene, stick on an acyl group, what you've got, which is this baby here, is less reactive than benzene. So of course it stops. You know, unless you go crazy and start to heat the guts out of it, but you don't want to do that. So it all makes sense. Now there's another problem for you. You're probably quietly intellectually moaning and groaning, oh my God, I've got to learn this stuff, you know. And a few minutes ago there was something else that I had to learn, even though teacher said it's dead easy and you don't have to remember it because you can work it out. Well, in fact, you can work this one out as well. Because, let me show you what the story is. There's a trick to it. Let's go through all of these. Let's put a nitro group on. You notice something here. The key atom, the atom that's directly joined to the benzene ring, has a plus charge. And not only does it have a plus charge, but you could write a resonance structure like that. And obviously in this resonance structure, the ring has been depleted of electron density. What's the matter? Sorry? Ring. Obviously the ring, isn't there a famous book called The Ring by Tolkien? Very famous British all this was worked out in England, actually. It was worked out quite extensively at University College London.
Me too.
Those guys that place where I embarrassed myself by giving the wrong answer to where was neon discovered. I said Cambridge. Yes, no, it's the room next door. You notice something. Not only is there a plus charge attached to the ring, but you can write a resonance structure to suck electron density out of the ring. So of course it's deactivating. Let's go to the next one, SO3. Again, you can write a resonance structure that sucks electron density out of the ring. What about carboxyl? Once again, you can do that. What about ester? Well, I won't do ester because it's the same as carboxyl. Let's do aldehyde. And you can do it for ketone, you can do it for nitrile because maybe that's a little bit strange for you. What about this baby? Now this baby's a little different because again there's a plus charge on the key atom, the atom directly attached to the ring, but it's sucking electron density along the bond because it's a plus charge, so it's sucking electron density out of the ring. So of course it's a deactivating group. What about CF3? Well, you know fluorine is very electronegative, so all the fluorine atoms are sucking electron density along the bond towards themselves. The net result is that the carbon to which the three fluorines are attached is strongly depleted in electron density, and so it sucks electron density out of the ring, again by induction. So it's very easy to understand if some group is going to be a deactivating group. If the key p atom, the atom attached to the ring, is plus charge, it deactivates. If there's a multiple bond, so you can write a resonance structure with electron density being taken out of the ring, so you get a plus on the ring, of course the ring is depleted, it's deactivated. And all the deactivating groups, with the exception of the halogens and CH2Cl, all of them, with those exceptions, are meta-directing. So now, for a couple of dozen different groups, I could write down a benzene ring with one of these substituents. And all you need to know is this an activating or deactivating substituent? And is it a member of the activating ortho-para-directing? Is it a member of this very small group of ortho-para-deactivating, chlorine, bromine, iodine, fluorine, CH2Cl? Or is it a member of another big group, deactivating, meta-directing? And as soon as you've decided that, you can write down what the expected products would be. It's essentially a no-brainer. But it's a little more complicated than that, because supposing I give you, which I certainly will, a benzene ring with two substituents on it. Now, what's going to happen? Each substituent will want to, depending on which group it's in, it will want to exercise its normal preference. Now, sometimes, depending on the nature of the two substituents that are already on the ring, and depending on where they are with respect to one another, they're either ortho, meta, or para, the preference of one group for a certain position or positions will be exactly the same as the preference of the other group. Then there's no problem. However, sometimes one group will want to stick a group, the next electrophile here, the other group will want to stick it there. So which one wins? So let me explain how to deal with that. It's quite easy once I've explained it to you.
Then you don't really have to pay attention.
Now, before I explain that, just let me make sure that you're absolutely ready to understand what I want to tell you. I've done two things so far when it comes to electrophilic aromatic substitution. I've told you how to carry out an electrophilic aromatic substitution on benzene so that you could convert benzene into nitrobenzene or into benzene sulfonic acid or into an alkyl benzene or an acyl benzene or bromobenzene or chlorobenzene. I told you how to do that. I then told you that if you take one of those products and you carry out a further electrophilic aromatic substitution, you have to think about two things. One is the substituent that's already present on the ring, is it activating or deactivating? And I wrote down three categories: a large category of activating and ortho-para-directing groups. And all of those apart from the alkyl group, all of those have the ability to push electron density into the ring. Usually that ability arises because they've got a lone pair on a heteroatom. So they activate the ring, and for reasons that I haven't yet told you, but you don't need it for the exam, but I'll certainly deal with it in the Friday lecture, those activating groups direct ortho-para. There's then a very small group of deactivating substituents that also direct ortho-para, halogens, together with CH2Cl. And finally, there's another large group which are deactivating and meta-directing, and I've explained to you why they're deactivating. They have the ability to take electron density out of the ring, either by induction or by being able to, allowing us to write a resonance structure in which there's a plus charge on one of the atoms of the ring. Now, if you've got two substituents on the ring, you need to place those two substituents into one of three categories. Either ortho-para directors, or alkyl groups and halogens, or all meta-directors. And you have to do it in this order. Ortho-para directors are at the top, all meta-directors are at the bottom of this short list. So, if you have two substituents, and supposing one of them is here, and the other one is here, this one wins. If you have two substituents, one is in this group and the other one is in this group, this one wins. If you have two substituents, one is in this group and one is here, this one wins. So there is a hierarchy. If the two substituents belong to different groups, then the orientation of the higher ranking class predominates. And all ortho-para directors beat out meta-directors. However, if the two substituents belong to the same group, then as one textbook puts it, all bets are off. You're going to get a mess. You're going to get a complex mixture. So let me show you how to do these sorts of predictions when you've got two substituents and you want to find out what's going to happen. So let's have a look at this. I want to carry out an electrophilic aromatic substitution. So what I do is I see they're two substituents, I see they're the same, and then I have to ask myself a few other questions. The top one, what would it like to do? The top one would like to direct another electrophile into the ortho position or the para position. Well, the para position to the top one is here, so it's blocked. So it can't do that. So this one would like to direct now to the ortho position. There are two ortho positions, but by symmetry they're the same. So this baby would like to direct there. What about this one? Well, exactly the same argument. This would like to direct para, but the para position is blocked. This would like to direct ortho. There are two, they're the same. So the top methyl group wants to, let's number it. The top methyl group would like the electrophile to go in position 2, and the bottom methyl group would like the electrophile to go in position 3. Which wins? You don't have to ask that question because by symmetry, 2 and 3 are the same. If you put a nitro group at position 2, and yet for another molecule put a nitro group at position 3, you'll get the same compound. So this is very easy to do. Supposing we'll do a nitration just for argument's sake. That's what you get. So although I said if two groups are members of the same class, all bets are off and you get a mess, in certain cases where there's symmetry, that isn't true. But now let's do one where it's not symmetrical. Now you see, you will get indeed a mess. Or you'll get a mixture at any rate. Because by the arguments that I've given, each of these alkyl groups wants to put a substituent ortho to itself. And these two compounds, they're isomers. They're not the same. Okay, now let's put two groups on that are on in different categories here. Okay, we've got two substituents. One of them is an ortho-para-director. The other one's also ortho-para, but it's alkyl. So according to this little idea, this is the dominating substituent. And this wants to direct ortho-para. Para position's blocked. It wants to direct ortho and ortho. The two ortho positions are the same. And so if you do a nitration, say, oops, the main product will be that. Now what happens if the two groups on the ring are not in the para relationship? Supposing they're ortho. Well, let's see what we can do for that. It's exactly the same logic. Let's see what we can do. Let's do that. So 1, 2, 3, 4, 5, 6. I've got two groups. In this set of this hierarchy, this is going to be the dominant group. This baby wants to direct ortho-para. Here's one ortho position. Here's another ortho position, but it's blocked, and that's the para position. So in fact, if you do a nitration of this, you'll get two compounds. Now suppose these groups were not ortho, suppose they were meta. Well, let's see what happens. I don't know what happens, I'll work it out for you. So I want to find out what will happen if I do, say, a sulfonation of this stuff. Well, I notice there are two groups. I'm able to identify the senior group according to this hierarchy, and it's this baby. And it likes to direct ortho and para. And in point of fact, you'll get some nitro here, some nitro there, and it turns out rather little here. And the reason is it's not so easy to squeeze an electrophile in between two other substituents. So you can see how to work out what you get when you have two substituents present. You ask yourself, which of these three groups is the substituent in? So you know which is the dominating substituent, and its preference is the one that predominates. Now I haven't given you you need to know this for the exam, it's on the exam. And I'll go through it again, plenty of examples in the help. You don't need to know the reasons yet, because I haven't done the reasons. You will know them by Friday, because I'm going to go through the reasons, and it's all understandable in terms of